Okay, last lesson of the chapter, 5.5. Our last and final quadrilateral is a trapezoid. All right, just two theorems today. So last class we talked about special quadrilaterals, and I made the statement there's truly nothing special about them. If we talked about this chapter in general, we talk about parallelograms, and then we talk about the other five quadrilaterals. All right. So from last class, we had the all the consequences of being a rectangles, the diagonals congruent. These were the above and beyond them being parallelograms. And for a rhombi, remember diagonals are perpendicular and the diagonals bisect their angles. All right. And then lastly, for squares are rectangles, and squares are also rhombi, therefore they include the consequences of being rectangles and rhombis and parallelograms. Okay. There was a couple of those other theorems. This is the one that you need to remember mostly. The one that's used the most in our book is that if you have a right triangle and you have a segment that goes from the right angle of a right triangle to the midpoint of the hypotenuse, the opposite side, it makes three congruent parts, ZM, XM, and YM. Okay. And then that last one we did, which was if you have a quadrilateral, right, that is also a parallelogram, and you know that one of the angles is 90, then they're all 90, which makes it a rectangle. I lied. The last one was 517, which stated if you have two consecutive sides of a parallelogram, and if they are congruent, then that makes it a rhombus. All right. Today's class is on none of those, and if I were to say a special quadrilateral, one that's not like the others, it would be this one. This is the one that I would call a special quadrilateral. All the other ones are similar to parallelograms, whereas this one is not. All right, so one more, the trapezoid. All right, by definition, a trapezoid is a four-sided shape, so it makes it a quadrilateral with exactly one pair of parallel sides, which means it's not a parallelogram. So we don't get those five consequences of being a parallelogram. We get other consequences. All right, so one set of sides, top and bottom or left and right, are parallel. And that's what makes a trapezoid. All right, so a couple names. So hopefully this is stuff you remember from pre-algebra. So the two sides that are parallel, we call those the base, which means we need names for the other two sides, and the other two sides shall be called legs by definition. Now, problem number one for most elementary geometry students is they always think the base is the bottom. I can take a trapezoid and turn it on its side. The base is not always the bottom. The base or bases are the two sides that are parallel. All right, we have a special kind of trapezoid, and that's where if the two legs are congruent, guess what we're going to call it? Two sides are congruent. We're going to call this one an isosceles trapezoid. And then there's one more. If you get a right angle on your trapezoid, in fact, we'll get two right angles. They only ever show one. Oh, and why is the second one? Let me diagram this one. Why is this one also 90? It's never shown to be 90. Well, let's see. It's a parallelogram, so same side interior angles, two lines, two parallel lines cut by transversal. Uh, uh, Same side interior angles are supplementary. So if one's 90, the other one's 90. Okay, so this one needs a name, and we will call this one a right trapezoid. So the first one on the left, that's just called a trapezoid. The one in the middle is isosceles. The one on the right is called a right trapezoid. Make sure that's in your book of truth. All right, let's prove something. So it's very hard to prove something about the other than the formula for area. We'll have a whole chapter on area. We're not there yet. That's very hard to prove something for about just the general trapezoid, but we can certainly prove something about isosceles trapezoids. So let's see, isosceles trapezoids, let's prove something. We're going to prove something about those four angles, the two red ones and the two green ones. So we're going to call those angles the base angles, right? The two red ones and the two green ones. And by visual inspection, the red ones look to be obtuse and the green ones look to be acute. So let's see if we can prove something. And this only applies to isosceles trapezoids. Okay, So we are going to prove that the base angles are congruent. Not they're all equal to each other, but the two tops and the two bottoms, or so the two base angles of one of those parallel sides, x and y, are congruent, and the other two, b and a, are also congruent. All right, so let's see how we can prove this. Well, it is an isosceles trapezoid. So maybe we could make some triangles and prove something. So I'm going to make two right angles or two right triangles. You see the two I'm making right there? So I drop a perpendicular straight down from point B and I drop a perpendicular straight down from A. It's a perpendicular that makes it two right triangles. We have that one theorem that states that the distance between two parallel lines never changes. So then that would mean that BP and AQ are in fact congruent. That's theorem 5.8 if you remember. And hopefully you're yelling at the screen. Therefore, if those are congruent, then the two triangles are congruent by our ever popular HL. Okay, cool. They're congruent. So what? Well, then that would mean immediately by CP/CTC that X and Y are congruent. All right, we're halfway there. Now we just need to prove that B and A are congruent. All right. Well, also by CP/CTC, those little tiny parts of the top triangle, right? XBP and YAQ, those would also be congruent by CP/CTC. And then, can you see it? Do you see it? So we have alternate interior angles because of or we have a rectangle. How about that? You could do it the other way as well too. We have a rectangle, the inner side, and we know that for rectangle, all the angles are congruent, right? Therefore, that means that angle B and angle A are congruent. Now let me prove that I'm combining steps. Kind of ran out of space. So if B or P, B, A, Q are a rectangle, that means this is 90 and this is 90. And we already proved by CP/CTC that this is congruent and this is congruent, right? Therefore, 90 plus the congruency is equal to 90 plus the congruency. Therefore, by the angle addition postulate as well, therefore, B is congruent to A. All right, cool. That was a pretty slick proof right there. All right, so what do we just prove? That we proved that the base angles of just an isosceles triangle are congruent. We didn't say anything about just a normal trapezoid or a right trapezoid, but for isosceles trapezoid, the base angles are congruent. Now, I want you to notice it doesn't mean that X is congruent to B, right? X is by observation, A or visual inspection is acute, and angle B is obtuse. But the base angles themselves are congruent, B and A and X and Y. Okay. Here's another idea. So we'll start off with a trapezoid, and I'm going to find the midpoint of leg SP. I'll label it M. And then I'm going to find the midpoint of, well, the consequence, I made two congruent parts. And then I'm going to make the midpoint of RQ. Now notice I can't put one tick mark. It would be true if it was isosceles, because the legs are congruent. But this one is just applies to all trapezoids. And then I'm going to connect point M and point N. So what have I made? By definition, that thing right there, by definition, it connects the midpoints of the two legs of a trapezoid. By definition, that's called a median. So make sure that goes in your book of truth, and then we'll prove something about that median. Okay, so here's the proof. The proof is it's going to feel like we did this with a triangle a couple days ago, and we did. Now we're doing this with a trapezoid. We're going to prove that median is parallel to the other two sides, two bases, and we're going to prove that it's one half of the sum of the two bases. All right. So that's I got to do two things. I got to prove that the median MN is parallel to SR and PQ. And then I need to prove that it's one half of the sum of SR plus PQ. All right, let's get to it. All right, so here's what we're going to do. We're going to extend SN. You see where SN is, right? We're going to extend SN all the way down to where it would intersect with a line extended from PQ. So I extend PQ out to an infinite distance, and then I extend SN out to an infinite distance, and where the two lines will intersect, we'll call that point T. All right, that's just a basic construction. Clearly, I've made two triangles. All right, and I'm going to immediate claim that those two triangles are congruent. And the question is why? So let's think this through. Well, let's see. So if we have two parallel lines cut by a transversal, then we know that the alternate interior angles are congruent. I got that and that. What else do I have? Well, let's see. So if you have two parallel lines cut by a transversal that makes congruent parts here, which it does because M was the median, right? Therefore, it cuts the other sides. That means that this is congruent to this. I should put two because we can't conclude that it's equal to the opposite side. Okay. What else do I have? Let's see, what else do I have? And we're going to claim an ASA. So we would also have that two parallel lines cut by transversal. Therefore, oops, I'm not drawing. Then we would have that this is congruent to this. That would be true. That's not part of my triangle. I need another angle. Oh, I got vertical angles. Do you see that? So this, I got to use two, would be congruent to this. And there's my ASA. Okay. Yeah, yes. All right. So well, I'm clicking when I shouldn't be clicking. So we have that those two triangles are congruent. Therefore, by CPCTC, N is the midpoint of ST by CPCTC. Okay. And I'm talking about, I'll highlight it right here. I'm talking about this part and this part, right? So they are by CPCTC. Okay, moving on. All right, so I'm going to immediately claim that therefore I've done the first part of the proof that MN is now parallel to PQ and MN is parallel to SR. The question is why? How did I just prove that? Well, we're going to go back to that one theorem a long time ago that says that if you have a triangle, let me draw this, I'll do it in red, that if you have this triangle right here, and you connect the midpoints of the triangle right here, therefore this right here must be parallel. This must be parallel to this. And then on the other side, we have the same shape of the just two separate triangles. Therefore, it's the same thing as 511. So 511 states that if you have a triangle where you connect the midpoint of one side to the midpoint of the other side, then it's parallel to the third side. So we have a triangle there. Let me draw it in blue, the other triangle. So the red triangles that would apply, and then for the blue triangles that would apply as well too. Okay. All right. Okay. So if that were true, why did I delete that? I wanted to leave that up there so you could see. If that's true, we're looking at this triangle right here. If that's true, you now have that medium of the triangle right here. We have that one theorem that says that therefore this side right here is equal to 1/2 of that whole thing on the bottom, right? So now I can make this statement right here. So Mn is equal to 1/2 of the entire thing PT, right? Okay. Now let's think this through. We're almost done, right? We got Mn. We're looking at this statement right here. We're trying to get to this right here. We got the MN, we got the half, but we have PT instead of PQ plus SR. So somehow I need to get rid of the PT and get a PQ plus SR. Well, I can see the PQ. The PQ is right here, right? Why are you not doing this? There we go. The PQ is right here, but I have a QT right here. But since we showed, and I'll do this in red, since we previously showed that this triangle right here is congruent to this triangle right here, then I could substitute instead of QT, I could substitute SR because by CPCTC, they are in fact congruent. So this is just segment addition postulate that PT is equal to PQ plus QT, and QT is equal to SR by CPCTC. And that big hot mess of a proof is now done. All right, cool. So what did we just prove? Clean it up. we proved theorem 519 that says that if you have a trapezoid, not an isosceles, by the way, we just did the proof, right? That if you have an isosceles and you have the median of an isosceles, then therefore that the median Mn is parallel to the two bases and that it's equal to 1/2 of the sum of the two bases. All right. So if you have a medium, it's parallel to the two bases and it has a length equal to, and it says the average, that just means the two bases added together divided by 2. All right. Don't forget that we have a similar one, looks like this, right? We also call that the median of the triangle as well, too. So you have trapezoid medium, you have the triangle midpoint is what they call it, but you could call it the median as well, too. So those are very similar to each other. For the triangle one, EB is equal to 1/2 of DC. And for the trapezoid one, MN is equal to the half of the sum of SR plus PQ. All right. Make sense? Cool. So how we do this, we'll just do one quick example or a couple quick examples. Sometimes it's hard to see where the question mark is, like which one is the question mark is sitting right here. Does it apply to the bottom or does it apply to this part right here? And so I will generally just look at the other bits of information. Well, 47 clearly is GD, and I have this 13 right here, so that must be FE, which means the question mark must apply to the median right there. Or actually, we don't know that it's a median. I'm telling you it's the median. When you do the homework, it will tell you that ST is the median. Okay, so let's see. Well, from the previous theorem, it says the median is equal to 1/2 of the sum of the two bases. Okay, so let's see, 1/2 of the sum of the two bases. That would mean that ST is equal to GD plus FE divided by 2. GD is 47, FE is 13. That gives us 60. 60 divided by 2 is 30. This is not a very challenging thing to do. It only becomes challenging when there are not numbers, but there's variable expressions. Okay, we'll do one of those as well too. All right, how about for the median itself? Let's see. So the median KL is equal to ED plus FC. That would be 11 plus 13, which is 24, and 24 divided by 2 is 12. Nice and easy. There's always a but, and the but is, well, what happens if we're solving for one of the legs, I'm sorry, one of the bases instead of the median itself. So this is just an algebra thing here. The setup is still the same. So the median is equal to GF plus HE divided by 2. This time I know what the median is. The median is 27. So it's just an algebra problem right here. Let's see. I would not get rid of the 23 by subtraction because really that's 23 divided by 2, and I don't want to mess with fractions. So I'm just going to clear the fraction to start with. I'm going to multiply both sides by 2. So that would be 54. The 2's would cancel on the right side. 2 times 27 is 54. And I subtract 23 and I'm done. All right. Even if there were decimal numbers, this is pretty straightforward. And the median is equal to the average of the two bases. So KL is 7, JM is unknown. Multiply both sides by 2, clears the fraction. And then subtract 7, you're done. All right, they will also give you ones with variable expressions. It's just an algebra problem. The logic is still remains the same. Notice they turn this trapezoid sideways. I can see that the mid part there, that 10, is a median. Why? Because look, the other two sides are cut in half, 7 and 7 and 6 and 6. Therefore, I can use this theorem. So let's see, that would mean that the median 10 is equal to the sum of the other two divided by 2, except the other two are variable expressions. Don't panic, right? So that means 10 is equal to x minus 3 plus 2x minus 4. X and 2x is 3x. Negative 3 and negative 4 is negative 7. And then we just simply multiply both sides by 2. Add 7. Divide by 3. They could ask this question one of two ways. They may actually ask you to use that 9 to figure out the length of the two bases. So see, the top base is 6. 9 minus 3 is 6. And the bottom base, or the base on the left there, is, let's see, 18 minus 4 is 14. So they could also ask the question that way. And that does it. We've arrived to the end of the chapter, right? Here's your homework. As always, if you have any questions, ask away. We'll end right here. And remember, the next step is to ask for the practice test and the test. I will see you in class.